let's start with problem number 5, okay, which we looked at today morning, right? Did you have a chance to work it out? What happened?
Use the differentiation in S2.
Yeah, but then what did you observe? No.
As in, it just seems to be another function.
Yeah, but what can you say about the magnitude of the output as t tends to infinity?
As t tends to infinity, the function I got is half t sin. So it will go to infinity.
The magnitude goes to infinity, right? Very good. Okay. Anyway, we'll work it out, right? So then what did you observe for problem number 6?
Problem number 6, as t tends to infinity, it oscillates.
It is bounded. Is it bounded? Okay. So now, we see that, we are getting some interesting results, right? I would say. Okay. So let's do these problems. Then we would essentially make some observations and do a general derivation as far as what we call as BIBO stability is concerned. Okay. That's going to be the objective of this session. Okay. So let's start with problem number 5. So we already know that for problem number 5, the plant transfer function is going to be, right? So it is essentially 1 divided by s squared plus 1. So we had a pair of poles, system poles or plant poles at plus or minus j. Okay, that's essentially purely imaginary poles, right? And we saw that when it was subjected to a unit step input, the output was bounded in magnitude, right? So that's what we observed in the morning. Okay, so now let's subject it to a cosine input, that too of a very specific angular frequency. Okay, the angular frequency of the signal is 1 radians per second, right? In general, cos omega t means omega is the angular frequency in radians per second, right? Cos t means omega is equal to 1. Okay, so that's what we have. So if u of t is cos t, so u of s is going to become s divided by s squared plus 1. Okay, so that's what we are going to have. So this implies that y of s, which is equal to p of s times u of s, that's going to be equal to s divided by s squared plus 1 the whole square, right? That's what we are going to get. Now, how do we get the inverse Laplace transform? We use a property of Laplace transform. Okay, so that's what we use. And as he said, you could use the complex differentiation theorem. That's essentially going to make our life very simple, right? If you recall, what was the complex differentiation theorem? It is essentially the Laplace of t times ft was minus dfs by ds, right? So let us say I take ft to be equal to sin t. Okay, so I know that the Laplace transform of sin t is going to be 1 divided by s squared plus 1. Okay, so now dfs by with respect to s, the first derivative of this function with respect to s is going to be equal to d by ds of 1 divided by s squared plus 1, right? So what is this going to be? I am going to get s squared plus 1 whole square minus 2s, right? That's what I am going to get. Do you agree? Okay. So consequently, if I do minus df ds, it is going to be, this minus sign is going to vanish, right? So that's what I did. Okay, so I just evaluated minus d of df s ds, right? So that's going to be plus 2s divided by s squared plus 1 whole square. So this immediately tells me that the value of y of t is going to be equal to 1 by 2 t times sin t, right? Why? Because the Laplace of t sin t is 2s by s squared plus 1 whole square, right? From this property of Laplace transform, correct? So the Laplace inverse of s divided by s squared plus 1 whole square is going to be 1 by 2 of t sin t. Okay, so that's what we are going to have. So immediately we observe that as t tends to infinity, we observe immediately that the magnitude of y of t tends to infinity, Do you agree? Correct? Okay. Now we do problem number 6. Okay. Problem number 6, we already know that the plant transfer function is going to be equal to 1 divided by s squared plus s, which was nothing but 1 divided by s times s plus 1. Okay. So once again we have to do for u of s to be equal to cos t, sorry, u of t to be cos t. So u of s is s divided by s squared plus 1 whole s squared plus 1. So y of s is going to be equal to p of s times u of s, which we are going to get as what, s divided by s times s plus 1 times s squared plus 1. Okay, correct? So the s and s will cancel off. So what we are going to have is the following, right? So we are going to have 1 divided by s plus 1 s squared plus 1, right? So that's what we are going to have. Okay, so this will be a by s plus 1 plus bs plus c s squared plus 1. Am I right?
There will s equals 0 be a pole?
Okay, we are coming to that. Okay, we'll discuss that. Okay, so I was waiting for someone to ask me that question. Okay, we'll discuss this. Okay, yeah, that's a good point, right? So the question now, I hope interpreting his question, he's asking, would s equal 0 still be a pole, right? Because I cancelled an s and a s, right, in the denominator and the numerator. S equals 0 is still a pole. Okay, pole is a characteristic of the system or the plant. Here the cancellation of s was a mathematical operation which came in due to the specific nature of the input that we have. But in general, we have a more subtle idea which is called as a pole zero cancellation. We will come there, okay, when we essentially go deeper into control system design. Okay, so pole zero cancellation is an important concept, but here it is not so. Okay, this is not a pole zero cancellation, because why? What is the quantity that I am calculating? It is y of s, it's not p of s, right? So I am calculating y of s. 0 and minus 1 are the two poles of the plant. It so happens that based on the input that I give, there is a mathematical cancellation of s and s. Okay, that can happen. Okay, yeah. Okay. So now what is the partial fraction expansion of this term? What are we going to get for a? 1 by 2. Right, multiply both sides by s plus 1 and substitute s equals minus 1. What about b and c? Minus 1 by 2 and? For what is minus 1 by 2? B, is it? Okay. I am just writing down whatever our friend is saying, you please check. Okay. But anyway, I am sure, by now you would know how to do it, right? So, is this correct? Does anyone agree? Yes? Is it minus 1 by 2 and plus 1 by 2? See, how can you figure it out? You can take LCM and then equate the coefficients, or you substitute any two values of s you like and then equate. You will get two equations, two unknowns. That's about it, right? You could do it either way. Okay, so I leave it to you to check. Okay, but more important, residues are important. Okay, so but more importantly is the concept which I am coming to is essentially y of t. If you take the inverse Laplace transform, you are going to get 1 by 2 e power minus t, 1 by 2 cos t plus 1 by 2 sin t. Take the LCM, you are going to get s plus 1 whole square I think this is fine, right? So because we are going to get s minus 1 times s plus 1 is going to be s squared minus 1, s squared plus 1, you will get 2 and 1 by 2 cancels off, right? That's right. So what would you say now, right, as t tends to infinity? Oh, sorry. Bounded, right? So previously we saw that, like when for the same system, when we gave the unit step response, the magnitude of y of t tends to infinity, right? Now, like we give another bounded input. I'm sure you agree that cos of t is a bounded input, right? Is it not? Correct? So we are getting a bounded output. So the question is, what is happening, right? So let me essentially let's do this. Okay, so let's construct a simple table. So let's say a system, poles, input, output. Okay, so let's do this. So first let's take the system which had complex conjugate poles, right? So first let's take y double dot plus y of t is equal to u of t. Okay, the poles were at plus or minus j, right? Oops. Okay, so for this system we considered two cases, right? So when the input was essentially 1, what was the output? Output was bounded, right, as t tends to infinity, right? Now for the same system, when the input was cos t, the output was unbounded, right? Similarly, if we take this system y double dot t plus y dot t is equal to u of t, the poles were at 0 and minus 1. Here when we gave the input as the unit step input, the output was unbounded. On the other hand, we give cos t, the output was bounded as for all time t, right? Correct? Now, what do you think is happening here? So, would you call these systems as stable, unstable, or something in between? Both are unstable? So, in fact, it so turns out that if we use the definition of BIBO stability, right? What was the definition of BIBO stability? Let me pull it up. So let's go here, and I think this is something which we saw in the very first class, right? In the very first set of classes where I defined BIBO stability. So if you look at the definition of BIBO stability, right, what did we learn as BIBO stability? A system is BIBO stable if its output is bounded for all possible bounded inputs. Okay, the keyword there is all. That is for all time t and u of t such that the magnitude of u of t is less than or equal to a finite positive number m. Okay, we should have the magnitude of y of t should be less than or equal to a finite positive number n. Okay, so that is the definition of BIBO stability. Now, if we apply the definition of BIBO stability, like to this, what to say, these two examples, we should brand them as unstable, isn't it? Okay, but it so turns out that the first system, okay, like let me call it as S1 and S2. Okay, the first system S1, the output is unbounded only if we give a sine t or a cosine t, okay, as the input. For unit step input or any other bounded input like a sine or a cosine of any other angular frequency other than 1, okay, you can show that the output is going to be bounded. Okay, so let me repeat that statement. Okay, so let's take S1. Okay, we consider the system 1. It so turns out that if I give any other cosine or sine input, right, cos omega t, sin omega t, such that omega is not equal to 1, okay, then the output will be bounded. Okay, and the output is also bounded for a unit step input, right? Isn't it? Okay, because out of the standard inputs that we consider, step, ramp, sinusoid and impulse, right? Which two classes were bounded inputs? Step and sinusoids, right? Ramp and impulse are not bounded inputs. So please, you see, if you want to figure out, like output response to a an input and comment on stability, don't choose impulse and ramp, okay, because they are not bounded inputs, right, to begin with. Okay, so if we choose step input, S1 was bounded, the output of S1 was bounded, and if you choose sinusoids of any other angular frequency other than omega equals 1, okay, the output will be bounded. It so turns out that only when the input becomes a sinusoid whose angular frequency is equal to the magnitude of the poles, right, on the imaginary axis, the output becomes unbounded. Okay, so what was the magnitude of the poles? See, for this system, the poles were at plus or minus j, right? What is the magnitude of the pole? 1. So you saw that when the input is a sinusoidal signal, either cos omega t or sin omega t, with omega being exactly equal to the magnitude of this purely imaginary pole, right, for system S1, then we are going to have an unbounded output. Okay, so for that reason, some people will call this class of systems as marginally stable or critically stable. Okay, that is, the output is bounded for all possible bounded inputs except one set, right? Okay, so that is why people call it as marginally stable or critically stable. Now the choice is left to us, right? So in strict parlance, like the system is unstable. See, if we use the definition as it is, right, the system is going to be unstable. I hope you agree, right? But if you dig deeper, we see that like it is not, the system output is not unbounded for all bounded inputs, but rather a small set, right? So that's why people call it as critically stable or marginally stable systems. But yet, we do not want to design such systems in practice. Okay, if we encounter such systems in practice, we want to stabilize them. See, we will see that such systems can be like an undamped mass spring system. If you have an mass spring damper system where there is no damper, you just have a mass and a spring, you will see that the equation of motion will become like that, because the Cx dot term will go to 0. So then you will have mx double dot plus kx equals f, right? That's what this is, right? So without damping, like yes, like you are going to have, if you perturb, you are going to have oscillations that are bounded, but then the moment you give a step, the output will become unbounded. Okay, so that is the bottom line here. Now on the other hand, if you look at system S2, it has a pole at the origin, right? So if you have a non-repeating pole at the origin, you give a step input, the output is unbounded. Okay, but for all other sinusoidal inputs, like the output is bounded. Okay, that is the property of S2. Okay, so for system S2, you see that there is a non-repeating pole at the origin. Okay, so for such systems, the if you give a step input, the output is unbounded. Okay, but if you give a cos omega t or sin omega t bounded input, the output will be bounded. Okay. So once again you see that for one input alone the output is unbounded. Yes.
For every system having pole at origin, then this property will be
Yes.
and same goes for S1.
Yeah. Okay. So for example, if you for a class of systems of S1, if the poles were at plus or minus 10J, if you give cos 10t or sin 10t, the output is going to blow off, right, to infinity, right, as time t tends to infinity. That is the bottom line. Okay. But this is true only when you have what is called as a non-repeating pole on the imaginary axis. Okay. So this result is true only if you have for non-repeating poles on the imaginary axis. Okay, great. Okay. So if you have a non-repeating pole on the imaginary axis, this is going to happen, right? So this concept. Okay. If you have a repeating pole on the imaginary axis, okay. So what do I mean? Let's say if the system transfer function, for example, suppose if the system transfer function P of s were like 1 divided by s squared times s plus 1. Okay, can you see this green color? No. Okay, let me choose a different one. Okay, let's say let me choose this dark green. Can you see this? Is it okay? Yeah. So for example, if the system transfer function, I'm just consider as an example, right? If you have a repeating pole, okay, what are the poles of this transfer function? You have 0, 0, minus 1. Okay. So with repeating poles, this system is unstable. Okay, one can show that. Okay. Similarly, if you have another system where the transfer function is 1 divided by s squared plus 1 whole squared, the poles are plus j, minus j, right? Once again, this is unstable. So the above concept applies only to this concept of marginal stability or critical stability applies only if you have non-repeating poles on the imaginary axis. Okay, right? Then what happens for stability? Of course, I should be careful for BIBO stability. Okay, some people will use the term asymptotic stability. We'll see why. Okay. So these are terms that you would encounter if you take textbooks and then read through them. For us right now, the only notion of stability that we are looking at is BIBO stability. Okay, so that's why I'm using BIBO stability. Okay, you will find an equivalent term asymptotic stability. We'll see when it can be used and what does it mean, right? So for BIBO stability, all, okay, I'm underlining all poles of the plant transfer function must lie in the LHP, or other words, that is have negative real parts. Okay, that's one important thing. Okay, so that is we could observe it from example number 1 that we did yesterday, right? The poles were at -2 and -3. You take any bounded input, the output will be bounded. Okay, so that is a guaranteed result. Okay, so that is one thing. Okay, if there exists even one pole of the plant transfer function in the right of plane, Okay, that is have as a positive real part. Then the plant or the system is not BIBO stable. Or in other words, we will say it is unstable. Okay, let me call this as point number 1. This is point number 2. Let's point number 3. If there are repeating poles of the plant transfer function on the imaginary axis, okay. So what we call as the j omega axis, typically the imaginary axis is also called as the j omega axis, right, because S is written as sigma plus j omega, right. So the imaginary axis is called as the j omega axis. Even if there are repeating poles on the j omega axis with any remaining poles in the LHP, the system, if there are repeating poles with any remaining poles in the LHP, then the system is not BIBO stable. Okay, once again, right, as we just discussed, right, you could do the same exercise. Okay, like I leave it as homework. Okay, you try with u equals 1 and cos t. Okay, you would see that in both cases, doesn't matter which system you take, output will be unbounded. Okay, that is a guarantee. Okay, because you have a repeating pole on the imaginary axis. Now, if there are non-repeating poles of the plant transfer function on the imaginary axis with any remaining, with I think I should say with all remaining poles, right, with all remaining poles in the LHP, then the system is unstable, critically stable. Okay, this I leave it to you. Fine. So because most textbooks will say it's critically or marginally stable, but if we strictly apply the definition of BIBO stability, it's unstable, right? See, in stability there cannot be any compromise. Either a system is stable or it is not. That's it, right? So if we are strict to that extent, we should call this as unstable. But if you say, like, oh, come on, like it's the output is bounded only for one small group of bounded inputs, well, you call it as critically stable or marginally stable, right? So critically stable, marginally stable, like all those are equivalent terms that are used. Okay. So that's left. That's basically some two perspectives of how to interpret system stability when you have poles, non-repeating poles on the imaginary axis, including the origin. The origin is also on the imaginary axis, right? So yeah, yes, please.
You said that if it's
Yes, exactly. That's what we are going to show, right? Okay, good point. So, condition number 1, I wrote that for BIBO stability or asymptotic stability, all poles of the system transfer function must lie in the LHP. So, the question was that, like, if I have a system, I find the transfer function, and if I figure out that all poles of the system transfer function lie in the left of complex plane, is the system BIBO stable? Answer is yes. Okay, how? We are going to prove.